Okay, so let's do a little bit of a video talking about AC filters. So first of all, what type of filter have we got here? The capacitor, it's a passive filter because there's no power supply. Passive filters, of course, are going to have a gain of 1 or less. The capacitor in this case is coming after the resistor, tafter. So this is going to be our treble cut filter. Our treble cut filter, or some people would then call it a low pass. Okay, so we need to calculate the reactance of the capacitor. So reactance of capacitor Xc equals 1 over 2 pi Fc. Okay, so then it's just a case of slotting in the value. So 1 over 2 pi times 50 hertz times by the capacitor 22 times by 10 to the minus 9. Always obviously make sure you use your the multipliers there. Gives us 144.68 kiloohms. Okay, there, and then and here we are. We're asked to go at 50 kilohertz. That's obviously change by going up it by a factor of 1,000, so we're going to go down by a factor of 1,000, or you can obviously work it out again. So that's going to be 144.68 ohms. The break frequency for this, so break frequency equals 1 over 2 pi RC. Remembering that the break frequency is when the reactance of the capacitor equals the resistance of the resistor. So that's what it is. So we've got 1 over 2 pi times by, what was the resistance value? 2.4k. 2.4 times 10 to the 3 times by 22 nanofarads gives us just over 3 kilohertz. Okay, looking to plot that on the graph here. Most we can have is a gain of 1. So there's our gain of 1 here, and we've got 3 kilohertz. So this is going to be a two-line approximation. So look, so there is 1. So this one is 2. So this one is our 3 kilohertz. So we're going to put a cross in there like so, and reminding ourselves this is a treble cut. So we're looking to cut out the cut out the high frequencies. That's why it's called a low pass. So using a ruler, sorry about this, then we're going to draw a line like so. We can then draw a line at 45 degrees from this. If you want to obviously do it a little bit more accurate, then what we can do is, if that's 3 kilohertz, I can go up by a factor of 10, so it's a 30 kilohertz. The gain will have also dropped off by a factor of 10, so it's at 1, so it'll be 0.1. So then that will also, that's a poor line. Allow me to draw a line in at 45 degrees. So that's 45 degrees. Don't have to measure it, just need to make sure it's as best as it can be. Okay, then right, moving on. So which one we got here? So the capacitor here is coming before the resistor. So this is a base cut or a high pass. Okay, you don't need to say both, it's just one or the other. Break frequency as before, calculating this, so break frequency FB equals 1 over 2 pi RC. So therefore we've got 1 over 2 pi times by 6.2 times 10 to the 3 times by 9.4 times 10 to the minus 9 gives us a break frequency of 2730 hertz. We're looking to then do some to calculate the reactance of the capacitor when the frequency is 200 hertz and 20 kilohertz. So when it is at 200 hertz, Xc equals 1 over 2 pi times by 200 times by 9.4 times 10 to the minus 9 equals 84.65 kilo ohms. That's a bit rubbish writing, isn't it? 84.65 kilo ohms. And then going to 20 kilohertz, well, that's a change going up in frequency by a factor of 100. So therefore I'm going to take that down by a factor of 100. So that gives me 846.56. Okay. So, calculate the peak voltage at 200 hertz. So what we need to do is, at 200 hertz, we need to find out what the combination of the capacitor and the resistor is, so that when we do our ratio method, then we've got know what we're going to put on the bottom line. So, so that's going to be Z. So Z is equal to Z equals the square root of R squared plus XC squared. So we're going to have 6.2 K squared plus 84.65 K squared, all square rooted. That gives us a resistance of 84.87 kilo ohms. Okay, therefore then we look to calculate what V out is going to be. So V out is going to be, well, we're measuring V out across the resistor. So the resistor there is going to be our top line. Then the total combination of resistance and reactance is what we've just worked out, which is Z times by V in. So we're going to have 6.2 K over 84.87 K times by 10 volts equals 730 millivolts. Let's have a look to see whether we're obviously on the right track. This is 200 hertz. This is a base cut filter. So at low frequencies, well, we're at 200 hertz, we're well below the break frequencies. We shouldn't have anywhere near our 10 volts out, because that would be a gain of 1. So therefore we've got an indication that we're on the right track. For the break frequency, we can just do a quick approximation, which is going to be 70% of our maximum, or if you want to do it a little bit more accurate, it's going to be 1 over root 2 times by our V in. So that's going to be 1 over root 2 or 0.7 times by our 10 volts, which equals approximately 7 volts. Okay, drawing our graph. This is a slightly different graph. You can see this is a log linear graph. So the log linear graph, we have to obviously be a bit more careful. So we're still looking at our break frequency at 3 kilohertz. So there is 1 kilohertz to 3 kilohertz. There's 3 kilohertz on our graph, and then we know that at our break frequency we're going to have approximately 7 volts out. So 5, 6, 7. So there's our 7 volts out. So we need to join up our points, put a cross in there like so. So what we've got to do, what we've got there is we're coming in like so, like that. We can actually plot another point if we wanted to. I haven't looked at the mark scheme. I think this is only worth 3 marks, so I don't think it was actually wanting you to pop that in, but we can actually plot the point at 200 hertz if we wanted to, because we know we've got 730 millivolts. So there's the 200 hertz. If that's 1 volt, 2, 4, 6, 8. So we're going to have a point sort of around about there. So therefore, then we're going to have a line like so. Don't forget, the most important thing is we're going to start off with a gain of 1 above the break frequency. And this is obviously a log linear, and then at the break frequency we're going to be 0.7 of that value, and then as it comes down, then it's going to then curve off to 0. Okay, and that's our log linear compared to our 2-line approximation then on a log-log graph. Right, okay, so let's go on to onto a bandpass filter. Onto a bandpass filter, here we go. So a bandpass filter, then we're going to look to have a resistor there, we're going to have an inductor there like so, and our capacitor like so. Don't forget, in all of your diagrams, always good to label them up. So there's my input, there's my output, and don't forget, always put blobs where things are connected. So we know that this is going to be a 4.3k resistor. We know the resonant frequency is 225. We know this inductor there is 0.01 millihenries. Okay, and it also has a resistance of 0.3 of an ohm. So we need to calculate the value of capacitor. So we got F naught is equal to 225 times 10 to the 3, which equals 1 over 2 pi root LC. So yes, so some people obviously look to try and get rid of the square roots, but obviously I like to do things a little bit more methodically and what we've got, so we can get rid of the 1 over on this to start with. So we're going to have 1 over 225 times 10 to the 3 is equal to 2 pi root LC. Oh yes, we knew the value for that. So therefore then just taking the 1 over, so 1 over gives me, just working that out on the calculator, 4.44 times 10 to the 6 over, and then we can get rid of the 2 pi, so we've got 2 pi is equal to root, let's put the value for 0.01 times 10 for the inductor, times 10 to the minus 3 times by C. So therefore, getting rid of the square root this time, we're going to have 7, so working out what the 4.4 times 10 to the 6 over 2 pi, it gives me 7.07 squared over the so then we can then divide by the inductive value, so 0.01 times by 10 to the minus 3 is equal to C, which equals 50 nanofarads. So strategies they're very methodical, but it gets me the right results. So dynamic resistance, this is the approximate resistance at the resonant frequency of the combination of the capacitance and the inductance. So it's just gives you the approximate resistance of those two only. Okay, divided by RL and C. So we're going to have 0.1. Oh, sorry, beg your pardon. 0.01 times by 10 to the minus 3 over 0.3 times by 50 times 10 to the minus 9. Gives me 666.67. Okay. So that's our dynamic resistance of our. So we're now looking to calculate the bandwidth of this. Well, we know that Q factor is equal to F naught divided by the bandwidth, which is equal to 2 pi F naught L over RL. So we can find out what Q factor is by just slotting in the values that we've got, times by 225 times 10 to the 3, that's our frequency, isn't it? Times by 0.01 times 10 to the minus 3. There we go, divided by 0.3 gives us a Q factor of 47. Okay, so now we've got a Q factor of 47, so we can then slot those values in. Okay, so where are we going to take that now? Well, now we can obviously put in our values that we've got. So we know that we've got 47, so this is our Q factor. Q factor is equal to 225 times by 10 to the 3 divided by our bandwidth. So obviously rearranging that. So bandwidth then equals 225 times 10 to the 3. Don't know where that pen on the screen has come from. It gives us a bandwidth of 4.79 kilohertz. What does that look like? I know it's not a question that's obviously on here. So we've got some sort of graph that looks like that. The center point on this graph here is going to be 225 kilohertz. We've now just obviously worked out that the bandwidth. This is going to be the width. So if we go 4.79 kilohertz divided by 2 gives us 2.39 kilohertz. So therefore approximately this point here is going to be at 227.39 kilohertz. Now where's this point here? What amplitude is this point here? Well, if we then work out what V out at F0 is going to be, well, our top line is going to be our RD, because that's where we're measuring our output against. Our bottom line, remember, we've got R plus RD times by V in. Well, if we say that V in, we will let V in equals 10 volts. Then just so you can see for an illustration, 667 over 0.67 over 4.3k plus 667 times by 10 volts gives us an output there of 1.34 volts. So this point here is going to be at 1.34 volts. Whereas then if we take the amplitude at that point there, that is going to be the V out maximum times by 0.7. So in terms of this, it's going to be about 940 millivolts. Okay, I know it doesn't ask that in the question, but I just obviously thought that it would be worth us looking at that. Okay, super duper.